about increasing, decreasing, relative minimum, relative maximum, first derivative test, second derivative test, right? We already introduced that. We're going to talk a little bit more about it just to kind of solidify it, right? So we should be able to go through much of this pretty quickly because it's not brand new to you, okay? One of the things that we really didn't touch on a whole lot was the difference between the absolute or the global max or the absolute or global minimum. Now, the term global is often referred to as relative. Okay. So sometimes you'll hear it as relative, all right? So basically, if we look at this graph here, point B, this would be a relative or global, relative or local or global minimum. Okay, relative, local, global, all interchangeable terms. Okay, that would be a relative minimum point because all the points around it are higher, right? All the y values around it are higher. It's not the absolute minimum. Yeah. Are they using global as the same as absolute?
Yeah, that's what absolute is. I thought like absolute and global like for the
Yeah, I think you're right. Thank you for noticing that. So they're using global and absolute as the same, relative and local as the same. Okay, good. Thank you. Okay, so this is a relative minimum. It's not an absolute minimum because there is another point in this particular example down here at point D where we have an absolute minimum. This is the lowest point on this curve that you're looking at. Okay, and the same thing here, if you look, we have a relative maximum here at point C, but we have an absolute maximum at point E. Okay. And even if you look at the endpoints, right, this endpoint here at A, it's not as high as this point at E. So this is a relative maximum. And the same thing over here at point F, this is a relative minimum. Okay. Okay. Let's move on down. Blah, 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 blah. All right. Noteworthy thoughts. Okay. When we say on an open interval, then we are not going to include the endpoints in our determination of our determination of extreme values. Okay. If it's a closed interval, then we have to also consider our endpoints. Okay. All right, let's move on down. So let's look at this example 3. Is this a closed interval or an open interval that we're referring to? Closed, because it's including the 0 and the 12. Okay. So find a relative extrema of f of x. So relative extrema means a maximum or minimum. Okay. Find a relative extrema of f of x. Can't find my spot in my notes here. There we go. Okay, so anybody have an idea? Okay, so let's make sure we state it correctly. So we're going to practice the phrasing because this is not a difficult concept like maybe related rates is, but we often lose points because we don't state things correctly and we make assumptions in our statements. So we want to make sure that we state it correctly and we're using the correct calculus terminology and justifications. So Let's actually just go straight across from left to right, okay? So we're going to say this point right here, right? What would we consider that? That's a relative maximum of 1 at x equals 0. Okay. The value 1 tells me the actual maximum value, the y value. But it occurs at this x value. One of the mistakes that we frequently make with these type of questions is we say, oh, relative maximum x equals 0. And that's entirely incorrect. Even though I know and you know what you're referring to, that will get marked completely wrong on your exam. And that would be really unfortunate because these are the easier questions. So we want to make sure we get these correct. Okay. How about at this point here? It's a global or absolute. I like to say absolute, but just because obviously I confuse the global term. Okay, so we have an absolute minimum of -2 at x equals 2. Notice I'm not using a point, right? I'm not saying absolute minimum at 2 -2, right? I'm phrasing it this way to avoid any confusion. Okay. How about at 5? This is not an extreme value. Okay. One of the ways, now we skipped over the formal definition, but the formal definition basically says, right, a relative minimum or an absolute minimum means that all of the surrounding values are higher than that. Right? All of the surrounding values are higher than that minimum point. Right? We said this is a relative maximum. All of the surrounding values are lower than that. So if we look at this point, that's not the case. Right? We've got some surrounding values that are higher, but then we also have some that are lower. So that is not an extreme value. Okay, and then at this point here, what is that? Right, that's an absolute maximum of 7 at x equals 7. Okay, and then we've got a relative minimum of 2 at x equals 10. You guys have a question? Okay. And then the last one, we have a relative maximum of 6 at x equals 12. Notice we only have one absolute minimum and one absolute maximum, right? Which makes sense. If it's the absolute, the largest value or the smallest value on the whole thing. Okay. Questions on that? Okay. So that leads us to what we call the extreme value theorem. Okay. What you really have to focus in on the extreme value theorem is that f must be continuous on the closed interval. Basically, if we have a continuous function, then we are guaranteed, excuse me, if we have a continuous function on a closed interval, we are guaranteed to have both a maximum value and a minimum value on that interval. Okay, the reason we say closed interval, if you can see my graph over here, right? Let's just pretend that this is my graph, right? What's happening at the ends? They're continuing. I do not have a closed interval. I don't have endpoints. This graph is continuing, so I do not have a maximum or a minimum, an absolute maximum or minimum. In this case, I don't have any maximum or minimum. Okay. Whereas if it was a closed interval, then that means I have endpoints. So I definitely have a maximum and a minimum. Yes.
So say, like, on the example before this one, if the whole thing, there's, like, an absolute, and then there's also, like, other relative ones, if you were doing, like, an interval on that big one, and with the, like, maximum or the minimum that would normally be relative, would it become global on that interval?
Yes. It could be, yes, assuming that it's still higher or lower than those endpoints. Yep. Okay. So here in example A here, example 4, letter A, right? The extreme value theorem does not apply. Why not? It's not continuous. Okay. Same thing here. Okay. Not continuous. Same thing on B. Does not apply because it's not continuous. How about C? Does the extreme value theorem apply? Yes, it does not apply because we have open intervals, right? Okay. And then here, the same thing. We have open intervals there, so it does not apply on that open interval. Okay. We good so far? Let's just take a moment. Let's go back. Now we have an intermediate value theorem, right? Because I want to make sure we reinforce this constantly. Intermediate value theorem has to be continuous on the closed interval. And the intermediate value theorem tells us that there's a point between the two y values. And we typically use this to prove that there's a zero in between where it switches from negative to a positive. Okay? Everybody recognize that? Okay. The mean value theorem, again, we're continuous on that closed interval, but here we also have to be differentiable. Our average rate of change will be equal to our instantaneous rate of change at some point. So the AROC is equal to the derivative at some point. That's the mean value theorem. Rolle's theorem, also continuous on that closed interval and differentiable. Rolle's theorem says that if I have two y values that are equal on that interval, that somewhere in between I've got an instantaneous rate of change that's equal to zero. Rolle's theorem can be used to show that there is a maximum or a minimum point on that interval. Okay. Sorry, I scrolled down too far. Yeah. And then the extreme value theorem, we're continuous on the closed interval, guarantees me an absolute maximum and an absolute minimum. Okay. Rolle's theorem proves that there is a maximum or minimum. We don't know if it's relative or absolute. Extreme value theorem guarantees me that there is an absolute maximum and an absolute minimum. Okay, so those are the four theorems that we've learned, and those are the four major theorems. Okay. Yes.
So all of them have, like, algebraic ways to, like, prove it. Is there going to be one for the extreme value theorem?
No. Well, let's look at example 5 on our notes, and then maybe that'll clarify some of that. Okay. Where did I go with that? Oh, that's the homework. Oops. There we go. Okay, so for each function below, justify why the extreme value theorem can be applied or why it does not apply on the given interval. Okay, so looking at this interval, -4 to 4, does the extreme value theorem apply? Yeah, Kayla.
No, because it's not continuous.
Right.
Because at 2 of it, it's going to be undefined.
Yeah, it's not continuous. On the interval between -4 and 4. Okay? Okay, how about this one?
Yes.
Is it continuous everywhere?
Yes.
Yes. Um, okay. So continuity is the only thing we're really worrying about here. Okay. How about C?
The only way to justify this is their continuity.
Yep. How about C? Is it continuous? Why not?
Because you can't, it would be an I imaginary number.
Right, because my interval includes these numbers less than -2. Okay, so we're going to say no, since h of x is not continuous for x less than -2. Did I say that right? Right. Okay. Or I should say, I should do it this way. I'm sorry, let me fix that. -6, x less than -2, like that. Okay? Yeah.
So I thought that you could still plot a negative, like the I on a graph. It just didn't pass the x-axis. Or is that like not?
No. When you're plotting imaginary numbers, you have to use a whole different plane. You have to use a complex plane as opposed to the real plane. Okay? Okay. So let's talk about there. Yeah. We've used that term critical number. We're going to just make sure we define it a little more clearly. Right? When we're looking at a critical number, we look at f prime. F prime of c is either equal to 0 or it does not exist. So, for instance, if I had f of x equals 1 over x minus 2, my critical number would be x equals 2 because it does not exist at that point. Okay? So critical numbers are where it either equals 0 or where it does not exist. Okay. So when we are proving or showing or justifying, I guess is a better way to say it, when we are going to justify the existence of an extreme value, right? When we're going to justify the existence of an extreme value, we can simply do that using the candidate test. We do not have to use the first derivative test. We can do it using what we call the candidates test, okay? Now, the candidates test, we have to figure out the critical points. Those are our candidates, okay? In addition to the critical points, our candidates are also going to include the endpoints. Okay, so we find our critical points and our endpoints. Those are going to be our candidates. So let's look at this example. I have to find my candidates on this. So what am I going to do? Right, take the derivative. Whoops. Mm-hmm.
Wait, so do they only find endpoints or also extreme?
Let's go through a couple examples and I think it'll clear up, okay? Take the derivative. So we have 24x squared minus 6x minus 9. Okay, now we're looking for those zeros, right? So we're going to factor this down, and this is going to factor as, let's see here, 6x, and will 3 work? Negative 3, positive 3. Does that work? Guess I could have factored out a 3 first. That would have made it easier, huh? 12. Yeah, that works. Okay. So we have x equals positive 3/4 or x equals negative 1/2. I made life hard on myself because I didn't factor out the 3. Okay. All right. So my critical points. My critical points are 3/4, negative 1/2. The critical points are the zeros and the undefined points. Okay. Okay, go back up. The critical points is where f prime is equal to 0 or f prime does not exist. Here, f prime is a polynomial, so it's always going to exist. Okay, so those are my critical points. So what I'm going to do, I'm going to do what we call a candidates test. And this is one of those things the AP score people like to see this, right? They just like you to say this candidates test. Just say it. Candidates test, and then we're going to do it instead of just putting the table there. It's just they just like to see that, okay? All right, so what points do we have? We've got negative 1. We've got negative 1/2. Where did I get the negative 1? The endpoints. The endpoints, right? The candidate test includes the critical points and the endpoints. I like to put these in order. Okay. These are my x values. I am simply going to plug them in and figure out what the y values are. That's all I'm going to do. And we're plugging them into f of x. So we're using a candidates test to do this. So f of negative 1, when we plug that in, we get 0. I'm going to save us time because I already have the values here. At negative 1/2, we get 4.75. At 3/4, I get negative 3.063. And at 2, we get 36. Okay, find the absolute extrema of the function provided the EVT is applicable. Well, the EVT is definitely applicable. It's continuous on that interval, right? So my absolute extrema, I have an absolute minimum. It said to find the absolute extrema. It didn't ask you to tell them where it occurs. What is the absolute minimum? Absolute minimum of negative 3.063. Absolute maximum of 36. Okay. Okay. Because it asked for the actual absolute value, not where it occurs. Remember that example we just did up here? We said the absolute maximum of 7 occurs at x equals 7, right? So it's not asking what x value it occurs at. It's asking for the actual absolute value. Okay, good question. Okay, look at letter B. First off, will the extreme value theorem apply here? Do we have an absolute maximum or an absolute minimum? Is the sine function continuous on 0 to 2 pi? Yes, it is. Okay, so that's the first thing we want to think about. Think it through. I should have done that up there, right? EVT, we don't have to say this, I'm just writing it for you. Guarantees existence of absolute extrema on 0 to 2 pi because g of x is continuous on the interval from 0 to 2 pi. Okay? Okay. So we have to find our critical points. So g prime of x equals 1 minus 2 cosine x. Okay. So I'm looking for a critical point, so I have to set this equal to 0. So we get negative 1 over negative 2, which we can just treat as positive, equals cosine x. Okay, where is the cosine equal to 1/2 on the interval from 0 to 2 pi?
60 and 120.
Okay, 60. Not 120.
Oh, wait, it's negative.
It's going to be down here, right? So it's going to be 60 degrees or 300 degrees. This is stated in radians, so we need to state it using radians. Okay? X is equal to pi over 3, or let's see, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi over 6, or 5 pi over 3. Okay? So now we're going to do the candidates test. Right, so we've got f and we've got g of x. So we're looking at 0, pi over 3, 5 pi over 3, and 2 pi. Okay, the 0 and the 2 pi are easy because we know the sign of 0 is what? 0. The sign of 0 is 0. So I have 0 minus 0, so this is going to be 0. Excuse me. At 2 pi, sine of 2 pi is 0, so I get 2 pi. Okay.
So you take the candidates test and apply it
To the
original.
original function, not the derivative. Okay, pi over 3. So what's the sine of pi over 3? That's going to be the square root of 3 over 2. We're multiplying that by 2, so it's the square root of 3. So I have pi over 3 minus the square root of 3. This looks like one that we really are going to need our calculator for. But let's see where we can go with it. Okay, so sine of 300 degrees will be negative square root of 3 over 2. And we're multiplying that by negative 2. So that's going to be a positive square root of 3. So we're looking at 5 pi over 3 plus the square root of 3. Okay, so it looks like in order to actually finish this, we're going to have to put it in our calculator. All right, so I'm going to assume that would have been a calculator problem. And actually, again, to save time, I already have it done. So this is going to be negative 0.685, and this would be 6.968, and of course this is 6.283. All right, so what's our absolute maximum?
Or 6.966.
That's right, absolute max is 6.968, and the absolute min? Good. Negative 0.685. Okay, put your 0 in front of that so that you don't have any mistakes with the decimal point. Okay. Okay, go ahead and do letter C. And just use your calculator if you need to, save you some time. Yeah, I do, yes. I'm hearing too much general conversation, so we're not using our time efficiently. Okay, so what's our first step? Take the derivative, yes. Did everybody do that? Okay, turn to your neighbor and share what you got as the derivative. Or turn to the person behind you. Everybody do it. Everybody do it. Okay, Manny, what did you get?
I got 2 cosine. 2 sine minus cosine x plus sine x.
With the help of you. Okay. All right. There's our derivative. Caitlin Nunez, what do I do now? What do I do now? Find the value of x at what when? Okay, so we have to set this equal to 0, right? Set that equal to 0. Yeah, see that now we're back to algebra, right? So we need to solve this trigonometric equation. So I'm going to factor out a sine x. It gives me 2 cosine x minus 1. I'm sorry, plus 1. So we're looking at sine x equals 0 and 2 cosine x plus 1 equals 0, which means we're looking for cosine x equal negative 1/2. Okay, on the interval, I still like to draw my little unit circle. It just helps me to visualize it. 3 pi over 2. So where is that going to be? That's going to be down here, right? That's what helps me, just seeing where it is on my circle. Okay. So we're looking on this interval here. So sine x of 0 is 0, right? Sine of 0 is 0, right? Did I do that right?
0.
Huh?
0 and
Yes. Yes. 0 and pi. Okay. Okay, cosine x equals negative 1/2. Where is the cosine equal to negative 1/2? So that would be right here, which is what? 2 pi over 3. Okay, It's okay if it takes you a couple minutes to figure that out, right? So remember, I go around, I'm like, this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, right? Each one, you're ignoring the pi over 4s, the 45-degree angles. Each one of these represents pi over 6. So here we are at 4 pi over 6, which is 2 pi over 3. And then the other spot is down here, right? So 6, 7, 8 pi over 6 or 4 pi over 3. So we have 4 spots plus the end point. Okay, so let's see our x value. So we got 0. 0 is also an endpoint, so that's good. So 0, and then I'm going to do 2 pi over 3, 4 pi over 3, 3 pi, oops, pi, sorry about that. Forgot about pi. Pi, and then 3 pi over 2, right? Remember, these are our endpoints. We've got to include the endpoints in there. Okay, and now I'm just going to use my calculator to come up with these values. Okay, let's see, we get -1. At 2 pi over 3, it's 1.25. At 4 pi over 3, I'm sorry, at 4 pi over 3, it's 1.25. At pi, we're looking at 1. And at 3 pi over 2, we're looking at 1. Do those values make sense? See, this is where I made a mistake. I didn't put them in order. Let me put them in order because then they'll make sense. This is going to be 4 pi over 3 right here. So this is 1 and then 1.25. Do those values make sense? Are you in radian mode?
I knew I was in radian, so I used the degree.
And you plugged in 120 degrees?
Yeah. And then the same thing happened with 4 pi.
Okay, let's do that together. It's important that we're able to do that. Okay, let's do sine x parentheses squared minus cosine x. I like to put it in y1 because then it makes, when I have, especially when I have multiple values to look at, to consider. Okay, I'm going to keep mine in radians. So we do, oops, let's try that again. Alpha graph. What is it doing? Sorry, press the wrong one. Alpha trace. Okay, y1 parentheses 2 pi divided by 3. 1.25. Maybe you put your sine squared in wrong. Okay, everybody, make sure you can do this. Let's do it now on your calculator, right? Because this is a shame when you get things wrong because of that type of thing, right? You understand the calculus, but then you make silly mistakes.
Can I show you what I calculated?
Yeah. I'm gonna make sure you can do it.
Just out of curiosity. What is y1? That's why I was trying to be lazy, so I got the change tracks in.
Well, you got what you deserved.
Unfortunately, we can't.
Yeah. Next question.
Anyone else having trouble? Make sure you're doing this. You really need to be able to do it.
They did the science way.
Signs, you mean, you just do sign, and then do your X in parentheses, and then do the square.
There we go. Okay. You put the equation in. So like this
Wait, so how do you do sword squares?
See how important it is to do this? Good.
Yes,
X,
square.
and then you do the square.
Yes,
Oh.
ma'am.
Yes.
Yes. And then this go back to sign X outside the parentheses or is it inside? Outside.
Wait, how do I do that, Miss Bird?
Parentheses X.
That's not.
How do you put the Y1 into that?
So you do. Make sure you're in radian mode. Okay.
Wait, so how do you get to radian mode?
You press mode, and then you choose radian. Okay.
Right is second.
Oh, I see.
Okay. Now to get Y1, you press the alpha and the trace button, and then you choose Y1. And then you do parentheses, whatever value you're trying to evaluate. So I want to evaluate it at x equals pi. And you can, if it's in your Y1, you can always go through and do the calculate value.
Yeah.
The reason I like to do it like this, let me turn is my thing on? Okay. Okay. The reason that I like to do it like this is when I have multiple values to do. Now I can just arrow back up to that, press enter, and then go over and change the value, right? So now I can change it to 2 pi over 3. Plus, I can see the history of those values. If you do the calculate value through the graphing feature, you're only going to see one at a time, and it takes a little bit longer to do that. So this is so easy now to go up and just keep changing those values. Right now we'll go over and we'll change it to the 4 pi. Okay. And then we'll change it to the 3 pi over 2. You see how easy it is, right? Okay. And enter. Okay. So let's go back. Now that we've got that, do those values actually make sense? Why? Because I have it's periodic. Yeah, it's periodic. A sine curve, right? Understanding the nature of our trig curves, right? They're periodic. Okay, so I have a minimum, an absolute minimum of -1, and we have an absolute maximum of 1.25. Okay. How much time do we have?
17 minutes.
No.
No, we have 15 minutes. 2 minutes.
Okay.
5 times 3. 4 minutes. Well,
How about letter D? How about letter D? Talk about this a minute, right? So I want you to form, let me see, the back corner, you guys can turn and talk to each other. Sophia, Logan, you guys can turn and talk to this whole row, so 5 of you. And then let me have the last 2 rows here, you guys can turn and talk, okay? I want you turning and talking, not working by yourself. I got some individual workers here. You're working with this whole row and Sophia. Okay? Yep. You guys can stand up. You can stand up and go.
We got Ben. We'll take Ben.
No, Ben's in the group. This is not a draft situation here. Stand up, form little groups and talk about it. Stand up, form little groups and talk about it. After you guys stand up.
Logan, stand up.
Everybody up.
We're in our group.
Everybody up. Stand up. Stand up.
We're in our group.
Stand up. Stand up. Stand
It's
up.
hard to write.
Stand up and talk about it. Yes, sir.
So I was doing public cadets, and so I got this disgusting answer that is a more complicated technique, but when I plugged in the graph, it was the same graph. If I like wrote down the less simplified answer, you would still take that on the test, right?
Yes, and it is the correct.
It is the correct answer. It's just written very
They
disgusting.
would take that, yes. Yep.
Everyone's going. That helps. You're not surprised.
Okay, what did you discover about this? It's not continuous.
Yes, because you can't take the natural log of a negative number.
There you go. Look at it first. Look at it first, right? EVT does not apply, right? It's not continuous. Where is it not continuous? Let's say -2, -1, 0, 1, 2. It's not going to be continuous. -2 to 3. Can't take the natural log of 0 either. No, natural log of 1 is 0. Right, it is not continuous. Well, -2 would give me 4 minus 9, which is a negative number. Can't take the natural log of a negative number. -1 is going to give me the natural log of -8. 0 gives me the natural log of -1. And of course, 1 and 2 give me the same. 3 gives me the natural log of 0, which I cannot do either. So it's not continuous on that interval. Okay? Okay. I think we will stop there. Let me give you homework because I don't want you to be bored.
I wasn't going to be bored.
So your homework will be 5.2. Did I load 5.2 in your thing? I'll do it right now for you then. Okay. 5.2. You're going to do numbers 1.
My mom has to because she looks at them every day because she's in charge of them. My mom can't even see them when the grades are off. It's not helpful.
A new one.
5.2, you're going to do 1 to 16.
Did you forget to say even?
Homework 5.2, numbers 1 to 16. I will load those right now for you.